Okay, excellent. Thanks very much, Chris. I'm very excited to welcome our speaker for today, Bruce Gemmell, and we're very happy to have you, Bruce. Bruce is joining us from Tasmania in Australia today, but he originally hails from West Canada, and he did his bachelor at UBC, and then moved on to his master and PhD at Dartmouth in the USA. But after this, Bruce made the big jump down under to the far south in Tasmania, where he started as a postdoctoral researcher at CODES at the University of Tasmania. At CODES, Bruce has since made incredible contributions to ore deposits research. He has worked extensively on epithermal deposits from around the world, both ancient and modern VMS systems, and also copper deposits, to name a few. So he has been recognised for his outstanding teaching contributions, and was appointed the director at CODES between 2012 and 2017. So with this depth and wide experience and knowledge, Bruce now consults on projects in Asia, Australia, and other parts of the world, as well as holding an honorary research professorship at the University of Tasmania. So we were very excited to hear your talk today, Bruce, on this exciting area of epithermal deposits in Indonesia, and hear your expert advice on exploration in this region.
All right. Hello, everybody, wherever you are, happen to be in the world, whether it's morning, evening, or afternoon. It's a pleasure to talk to you today. A special thanks to Alannah, Chris, and Neil Fernandez for inviting me to give this particular talk, and I'm looking forward to sharing some knowledge about a really interesting goldfield in Indonesia, the Gosowong low sulfidation epithermal goldfield. It's an area that most people don't get a chance to go to, but as I'll explain to you, it's got fascinating geology and mineral deposits in it, and it's a great exploration story, and it's also one of the world's richest low sulfidation epithermal goldfields. We're going to talk about the geology, the mineral deposits, and the exploration prospectivity. But what I'm about to present to you is not just work I've done. I've been really fortunate to work with a very talented group of people since about the year 2000 through about 2015 in the goldfield. Many people are shown here. The upper left is the team in 2000 when I first went to work on an Amira project looking at alteration on low sulfidation epithermal systems. And I had the chance to work with the Indonesian geologists there, including Dan Olberg that I've highlighted. And we'll talk about his work, which was instrumental in the discovery of the Kencana ore deposit a little bit later in the talk. The upper right is a group that from 2008 to about 2012, I worked with Newcrest on the property. Stephen Micklethwaite was a postdoc looking at the geology and structure of the district. Lindsay Clark did her PhD in the Kencana deposit. And Daud Silatonga was one of the Indonesian Newcrest geologists, and he looked at the Togarachi and Bora porphyry prospect as part of the research in the field. Then in 2012, Michael Roach, who's a geophysicist from the University of Tasmania, and his honors student, Michael Dunn, came on site, and they did a geophysical sort of magnetic work and magnetic inversion work, et cetera. And I'll show a little bit of those results as we go on. But this research, throughout the history of it, was funded by primarily Newcrest Mining, also Amira. Those of you that are not familiar, Amira is a group that brings researchers and industry together to fund projects where everybody collaboratively shares the results. And we had an Amira project on that low sulfidation alteration, and Gosowong was one of the areas that I worked on with it. Also, the funding for this project came from the ARC as part of the center's funding to the University of Tasmania and the University of Tasmania itself. So we're off to the Southwest Pacific. This is a beautiful part of the world, just north of Australia and to the west of Papua New Guinea. Indonesia is a fascinating country with a large number of islands, et cetera, and a large number of arcs, volcanic arcs. And where we're going is the island of Halmahera, which is located in this little area in here. It's sort of a K-shaped island. The Gosowong deposit is highlighted in there, and what's called the Halmahera Arc. The North Sulawesi and the Halmahera arcs are both late Miocene to Pliocene in age. And as I'll show you in the next slide, the tectonics in this area is incredibly complicated. It doesn't look it from this particular diagram, but it is. Also highlighted on this is not only where the various magmatic and volcanic arcs are, but also some of your favorite ore deposits that are distributed through these arcs, from the Kalimantan belt through the Sundabanda arc, et cetera, even through into the Grasberg deposit in the medial Papua arc, I should say. So it's a fascinating part of the world, right on the equator, hot, sticky jungle country to work in, but fascinating geology. So if we sort of zoom into the idea of the tectonics, we've got Halmahera Island, which is this area here, this sort of K-shaped body. And through here is Halmahera Island and the Gosowong Goldfield, and this contracted work in the little green square is located there. But what you can see right away is things are very complicated with faulting, also a whole series of subduction zones at various angles in through here. This is actually an area of a convergent arc or convergent arc system in through here. We've actually got subduction going in two different directions in here. We've got convergence, thrusting, and uplift in this area here with a lot of really shallow seismicity in through here. And we've got subduction going both to the west and to the east. And we've got active volcanic arcs down here to the west, and also the Halmahera Island in through here with an active volcanic arc running through there. You can see that the arc is being significantly dismembered by thrusting. What's basically happening from the south, we've got the Australia-Indo plate moving to the north, and over here on the eastern side here, we've got the Pacific plate moving to the west. And this has created this real convergence in this area here with subduction and going in different directions and a lot of different faulting, et cetera, going through it. So it's a fascinating area tectonically as well. But if we zoom into Halmahera Island itself, and this is a geologic map on the left, the island is basically broken into two different geologic domains. The area here on the eastern side and to the south of the island, you can see all in the blue and purple colors here. This is actually Cretaceous ultramafic rock and parts of the ocean crust. If you allow me to go back one slide, this is part of an oceanic plateau in through here, ophiolitic plateau. And the eastern side of the island actually contains some of those ophiolitic rocks right there. Those rocks also have lateritic nickel in it, and that's being evaluated, and in fact is being mined at times. I'm not sure if it's still being mined. Somebody might know later in the discussion, but that's where lateritic nickel is. The western side of the island in through here in the greens, that's the modern volcanic sort of Plio-Pleistocene rocks in through here with an active volcanic chain and the triangles running down. The red symbols are the modern volcanism. The yellow symbols are sort of more ancient volcanoes there, ancient being 10,000 years ago in that area there. The actual capital of the island system is on this island here, Ternate, which is a volcano itself. So the capital is actually built on a volcano. What is interesting, though, and will affect looking at the geology later, the shot up here in the upper right, this is Ibu volcano here, the helicopter's over, looking all the way down this chain towards Ternate down in here. And what you can see is you've got subaerial volcanism all in through here, but very quickly as you go offshore, you're going into seamounts that started life as seamounts and then become emergent, and you have subaerial volcanism. So the combination of the geology, the more recent geology in this area, is a combination of submarine volcanism and sedimentation and subaerial volcanism over top of that. So you've got this combination going on. The Gosowong Goldfield situates about right there under that cloud. There is active eruptions going on. This is Gemmell volcano erupting in 2007. So it's a tectonically active area. There's little earthquakes all the time, and it's quite a fascinating place to be. I'll mention it a little later, but this island down here does in fact have a very small porphyry copper deposit on it in here. So I'll mention that later on when we talk about the porphyry potential. As far as the district metallogeny goes, there are two styles of mineralization. The most important which is the low sulfidation epithermal gold and silver veins. This is the very high-grade mineralization that's been mined. Gosowong, Togarachi, and Kanchana are the three deposits that have been exploited so far. And the age dating on the alteration is about 2.8 to 2.9 million years old. So it's very, very young material. That epithermal alteration is actually superimposed on top of, in some instances, subeconomic porphyry copper gold prospects, Boro, Tabobo, Ngoli, and Matat. That porphyry alteration has been dated at 3.5 million years. So you can see in this photo the superposition and the light colors there of epithermal veins with their alteration halos superimposed on top of potassic alteration with very low grades of copper and gold in a stockwork vein system. Now you can see in only maybe half a million years or so, there's potentially been about several kilometers of uplift to superimpose these epithermal veins on what were deeper porphyry alteration. And that's beautifully exposed in the Togarachi pit here. Well, first of all, we're going to concentrate on the epithermal deposits. Now, this district is primarily sort of operated by Newcrest, but it's actually in a joint venture of 25% with another Indonesian company to form PT Halmahera, or PT Nusa, which is the group mining and operating this ore field from sort of its discovery up until just March this year. At the very bottom of the diagram, you can see that in March this year, Newcrest sold out its 75% of that joint venture to another Indonesian company for $60 million. And the reserves at that time were quoted as being 3.1 million tons at 10 grams per ton. It's still left in the district. But the main deposits of the gold field are shown here. The first one that was discovered was Gosowong, of a little under 1 million ounces, then Togarachi, a little over 1 million ounces, and the best and the biggest in the deposit in the district is Kencana, with a little over 4 million ounces of gold in it. So all up, we're talking about 6 million ounces of gold that has been discovered so far in the district. As far as the district geology goes, this is a very simplified plan map. We're dealing with Plio-Pleistocene rocks. We have Gosowong Formation in the light green, the Kayasa Formation in the blue. They've been intruded by diorite porphyries, and then we've got recent cover, which is, I'll show you in the strat section in just a minute. You can also see there's a very large number that have been discovered on the ground of veins cross-cutting through that contain quartz. Not all of them are mineralized, but there's a very, very large number of epithermal quartz veins in the district, and that's very common in these styles of districts. You can also see, however, a number of different other structures that are in those sort of orange, the fault lines getting through. We've got, and I'll talk about the structure in a couple of slides, but for the most part, the northwest and north-south faults or structures are the ones that are containing the bulk of the gold mineralization that's been discovered to date. So we do look at a stratigraphic column. This is something that Stephen Micklethwaite put together back in 2010. And this shows that we've got if you go from the sort of the bottom to the top of the main formations, we have the Gosowong Formation with a basaltic member, and then overlying that an andesitic member. Then we have the Kayasa Formation in the sort of the purples above that, and then overlying sort of everything are these quaternary deposits in yellow. The diorite does intrude into both the Gosowong Formation and the Kayasa Formation. You can see there that the rock types are primarily coherent volcanic rocks with volcaniclastics. One of the big differences within the andesitic member of the Gosowong Formation, we do get these hematitic mudstones, and they're quite influential in showing basically the rheology of the rock packages, that when they're faulting, or when they've been faulted, there's different rheology features across different rock packages, and this has allowed some of the veins to blow out, some of others to be constricted, and we'll see that as we go through the talk. The yellow material at the very top is all ignimbrites. It's got charcoal fragments in it. It's the most recent cover that's covered over the area. You can also see on this diagram highlighted in red where the various vein systems fit or cross-cut the stratigraphy. The main Togarachi veins are primarily down in the basaltic member and diorite, as I will show you. The North Togarachi veins are up into the andesite part of the package, whereas the Gosowong and Kencana deposits are all within the lower part of the andesite member of the Gosowong Formation. Example of what some of those rock types look like. Sort of from the bottom, you can see the diorite porphyry. Beautiful, some nice phenocrysts in through there. We'll see how it can be extensively altered a little bit later. We've got the basalt member of the Gosowong Formation shown with a coin for scale. Then we get into those hematitic mudstones, and they're very much showing us that we're dealing with a submarine package of rocks. Also within the andesitic member, there's graded mass flows as well as coherent rocks. One example, there's the andesite lava. Then we've got the dacitic pyroclastic fall, which is part of the Kayasa Formation. And then we've got the quaternary pyroclastic fall, which is the yellow rocks, which cover over their most recent ones and covering over a lot of the district. As far as age dating goes, we did a fairly extensive set of analyses here. This, again, was Steve Micklethwaite's work. The Gosowong Formation comes in at around 3.7, 3.8, 3.6, 3.7 million years in that case there. The Kayasa Formation is a little bit younger, down from 3.5 to mid threes. Then we've got the samples of the diorite in through there that are all around 3.5 to about 3.4 million years. So that's sort of the rock package we're dealing with, Plio-Pleistocene in age there. Then we've got in the sort of pink-colored, orangey pink-colored bar there, back in 1998, there was some age dating done on alunite in the advanced argillic alteration in the district and adularia in the Gosowong vein, and they both came in at about 2.8 to 2.9 million years. We then undertook dating of the adularia in Gosowong, Togarachi, and Kanchana, and there's a little photo there shows the staining of some of the Kanchana material showing the distribution of adularia. And we also got very similar ages, about 2.8 to 2.9 million years. So we've got an older at about 3.5, so sort of the diorite, and that's when the porphyry alteration's been dated in that, and then a much younger, or somewhat younger, 2.8 to 2.9 million years when the epithermal mineralizations occurred in the district. And interestingly enough, that alunite from the, and this is hypogene alunite from the advanced argillic alteration zones, that also comes in at 2.8 to 2.9. And that's some of the things we'll talk about when we look at sort of the metallogeny of the district near the end of the talk. As far as the deformational sequence in the area goes, Steve put a very nice sort of summary slide together along showing the different zones of the deformation. Really, we're dealing with north, northwest, northeast, and east trending structures in the district. So there's a number of different structures there. But the important ones, as we recognize to date, are the north and northwest trending structures, which seem to host most of the significant epithermal mineralization that's been discovered to date. There is quartz veining in some of these other structures, but it's not of great or economic significance so far. And you can see in Steve's summary diagram here that the stress fields have moved around. We've got different directions of extension, et cetera, going on faulting. But the most primarily one we're dealing with is the north-south extension, or sort of north-south trending veins with east-west extension. Now, the story of the exploration. Newcrest did a fantastic job in this district. The first discovery of Gosowong was in 94. Mining didn't commence till several years later. Then they discovered Togarachi 1, Kanchana, and then Togarachi 2. And that's all in the space of about they found over 6 million ounces of gold in 14 years 24 years, I should say, of working in through that area. So it's a lot of work's gone into this, and they've done a lot of great work. And I'll sort of walk you through a little bit of the exploration story. To begin with, the CRA back in the 70s did a stream sediment sample through the islands. They were looking for porphyry, copper mineralization. They assayed or analyzed for copper, but they didn't analyze for gold at that time. It wasn't until CSR came along about 10 years later that they did Blake stream sediment sampling. That was the time Blake was coming in for a lot of people to look at that. And they actually came up with some nice, interesting anomalies in the various creeks through the whole of the Halmahera Islands, but they didn't follow that up. It wasn't until the early 90s that Newcrest was looking around the Southwest Pacific for areas that they seemed to have the right geology to find porphyry or epithermal mineralization. They latched onto some of this older work. They realized there was they could get a good ground position and to explore through the Halmahera Islands, and they came in on the ground. So they picked up ground. They did reconnaissance stream sediment sampling, float examination, mapping, and soil sampling, and they came up with some pretty interesting stuff. The little diagram there, the map, shows the Bora porphyry system, the Tobobo porphyry system. This is what we now know as the Gosowong vein system in through here. But if you strip the red bits off this diagram, you can start to see some of the Blake samples in through here. And there was one that was 4.1 grams per ton. There was several others in this area. The first area that they actually got into to look for in this area was the Bora porphyry. That got a lot of their interest. And then they came back down into this area here, and I'll show you why they did that in the next slide. So 1994, they were working up the creeks and they were coming up the Tobobo River here. And this area right in here, the discovery outcrop, is shown below us down in here. This is a series of quartz veins, both quartz, crystalline quartz, and chalcedony, cross-cutting through altered andesite. And that assayed that outcrop of 20 meters at 4.5 grams per ton gold in the quartz veins only. In the upper part of the diagram here, you can see the whole outcrop itself, if you didn't selectively get the quartz veins, ran 20 meters at 0.6. Now, this is what brought them into the area. But to show you what it really looks like, this is a shot taken in 2012. This is what's left of the Gosowong open pit in the background. This is a bridge over the Tobobo River. This is the discovery outcrop down here. This set of rocks and rubble in the creek That's what the geologists first found, realized the potential, assayed them. You can see there's the discovery outcrop there. That then led them to finding 1 million ounces of gold in the Gosowong vein system. So you young people out there that are going to work in areas like this, don't think anything is insignificant when you're prospecting. They're coming up the creek, all of a sudden found a concentration of quartz veins they hadn't seen before. They're smart enough to sample it. That led them into this area. Then what happened is they started working their way up the streams. Quartzo Creek was right next door to it, and they actually started to find epithermal float in that area there. They worked and did soil sampling up this particular ridge, this area in through here. Here's the camp, and the Bobo River would be right down there. This is a ridge coming up here, and that's actually the ridge that contains the Gosowong vein system in through there. They trenched across these areas here. Well, I've been asked to start my video. I'll do that again. There you go. Hopefully this is still working, folks. This is the trench in through here. Trench 3 was a photo taken by some of the people just shortly after they did it. That trench ran 28 meters at 51 grams per ton gold. So they knew they were onto something very big. They stepped back. Their first drill hole under that trench in through here at 18 meters at 130 grams per ton gold. So they knew they were on to something very, very important and very rich. The next drill hole, however, number 2, down here, only hit 2 meters at 3 grams or 4 meters at 7 grams. So really not much going on. They drilled down below that and then hit 7 meters at 20 grams. What we do know now, this is an upper ore sort of lode within the vein system. This is a lower lode. This is what we call the next system, which was only chalcedony vein and had very little in the way of grade. An example of sort of one of the drill rigs in the area, and then again showing you just the spatial distribution where they did all the definition drilling to form up this particular deposit. This is what the Gosowong deposit looks like in the open pit when I first visited there in 2000. The resource from the drilling was a little under a million tons at 27 grams per ton and 38 grams per ton silver. So the gold to silver is about 1-to-1 in these deposits. The discovery outcrop was this area down and through here, and what we now recognize is what's called the quartz vein stockwork zone down in here. This is the trace and the dotted line of the Gosowong fault system running up through here. This is that deeper ore zone that we saw in the drilling. This is that sort of much lower grade zone in through here, the next zone of the chalcedony zone. And then this is the upper quartz adularia zone that had the very, very high trench in the first drilling in through here. Now you're going up probably about 150 meters from down there to up in here, up the hill. And basically you've got the upper part of the vein system exposed and the higher parts of the hill. And then the erosion is actually going down with the vein system down in here. This is, you can see the basically north-south strike zone. It dips at about 45 to 50 degrees to the east in through here. Examples of what the rocks look like of the two main ore zones are shown on the bottom. The quartz adularia, all the stuff that looks like this dark material in through here is a combination of pyrite and electrum. And then this zone in through here is the beautiful banded quartz chlorite rock, which is the lower ore zone down in here. And again, all the shiny material in through here is all electrum with pyrite. So very, very rich material. When you look at the geology of the Gosowong vein on this particular cross-section, about through the middle of the deposit, the vein is in the red. This is the quartz adularia blowout zone up to the surface in through here. This is the same drill section as before. This is where it sort of flattens out, where it hits these hematitic mudstones. Remember the rheology difference of the different rock types in here. Then it actually steepens down again. That's the quartz chlorite zone down in through here. And then you get down into the stockwork zone, which is on this particular section is down in here. And that's what was found in the outcrops of the river, was this sort of deeper part of the quartz stockwork zone down in through here. The host rocks are primarily andesite volcaniclastic rocks in the light green, andesite coherent lavas in the dark green, but then these mudstones come into play in through this. The whole area has actually been tilted about 30 degrees in places. And that's why things don't look exactly parallel or anything through here. So it can be quite complicated geology, and there's a large number of faults that have displaced the various lithologies at the same time. But what we do know is the steeper portion of the vein where had the greater dilation and also the greater grade. The work I did first there was to help them understand the alteration around the vein. I've spent a lot of my career looking at hydrothermal alteration. What I discovered from a lot of core logging and pit mapping was that there was various styles of alteration. In fact, most importantly, two different styles of propylitic alteration. The main alteration right in the vein and on the edges of the vein is quartz adularia, which is in that orange material there, and you can see some of the intersections through the vein in the background of that orange zone there. That's surrounded by argillic alteration, which is primarily illite quartz, some adularia, a little bit of chlorite, but smectite and pyrite, and that you can see that following down some of those subsidiary structures. And then we've got this lighter green zone. And what I discovered in all my logging was this was what I call vein-related propylitic alteration. And this turned out to be veins and veinlets of epidote, chlorite, smectite, calcite, and pyrite that only occur within about 50 meters of the vein. All of these alterations that I've just described are superimposed on top of this background regional propylitic alteration, which is the dark green. And that's primarily epidote, chlorite, albite, and pyrite. So there's a real, I'll show you textural difference, but a mineralogical difference between these different styles of propylitic alteration. So not all propylitic alteration is the same. You have to understand the mineralogy and the textures to differentiate them. What these various alteration systems look like. The upper part is the silicic alteration, nice bleaching of the rocks. These are andesites in this case that are not bright white. Of quartz and adularia. You stain it, you get huge amounts of adularia through the rock. We've also got fragments caught up in the vein with beautiful crustiform banding around them. Again, they're all quartz adularia altered fragments. The argillic alteration is illite, quartz, and pyrite. And this particular two examples here outcrop in the core sample of the coherent andesite, where you can see the selective replacement of the feldspars with illite and quartz. And there's pyrite all through the background. And the sample on the right there is basically a weathered example of core. And the pyrite's broken down to hematite, giving it that red color. Now, this is the vein-related propylitic alteration. The sample on the left clearly shows an epidote and calcite vein cross-cutting through a rock. It's got an alteration halo extending out to here, and that's superimposed on top of the regional propylitic alteration in the dark green here. So you can clearly see you've got veins with epidote in it, with an alteration halo on top of this background alteration. You can also see there's a lot more epidote right here than there is out in this particular zone here. And this is basically in andesite volcaniclastic rock. This is a finer grained portion of that andesite volcaniclastic rock. Again, with epidote, you can't really pick the calcite too well, but this is a little stockwork of these epidote veins cross-cutting through. And these only occur relatively close to the vein system itself. And that's shown in these sort of four slices of core as you're moving from near the vein to 50 meters away from the vein. And again, these veins, basically they decrease. There's a very high proportion of these veins and veinlets here, and you can see they decrease down as when you're 50 meters away. You just get a few little hairline fractures, but you still have that same mineralogy. And this alteration here, as well as the regional propylitic, is being overprinted by the silicic and the argillic alteration of the vein system itself. But you can still recognize these features. We do know now from work that this particular project showed up, other geologists around the world will know this and working around other porphyry and epithermal districts. These halos of this sort of vein-related propylitic alteration can be quite important if you're mapping in an area. So it's important to realize what the regional stuff looks like, but it's also what these fracture systems and stockwork zones can look like too. So you need to know the mineralogy, map them out, plot them on your maps, plot them on your sections, whatever you've got to work with, and see the distribution of it, because it could give you a clue that you're getting in towards a mineralized area. And then finally, the regional propylitic alteration is shown here. This is primarily selective alteration of the feldspars or mafics in this case, an andesite. You can see here from the photomicrograph, beautiful epidote, selective epidote alteration of feldspar. And there's a little bit in the ground mass, a little bit more chlorite in that particular case there. But it's very clear that you've got a very different style for this sort of regional selective alteration versus the vein-related propylitic alteration. But the point is, in this particular case here, the alteration does not extend that far away from the Gosowong vein system. You see the hammer for scale there, and the red is the vein and silicic alteration, the bright white material there. The argillic alteration is only about 1 meter wide in this particular example. This is an open pit. This is a photo from the old pit. And then when you get over to the right-hand side and through here, you can see the rocks have a distinctly green color to it. This is the regional propylitic alteration in the andesite in here, but you can see these little lines down and through here cutting through the outcrop. That's actually the vein-related propylitic alteration in through here, very close to the vein. And then as you move along the bench, as you move further out this way along the bench, you would see those amount and the intensity of that veining decrease right away till you get back out into regional propylitic alteration. A summary of that alteration mineralogy is shown here. Most of you will understand these minerals and their chemical formulas. The interesting part about it, if you look at this long enough, there's only about 6 elements that make up all the alteration minerals, if you exclude oxygen. So we're really just taking the elements that are already in an andesite, recombining them. We're adding potassium and some silica from the hydrothermal fluid, and that's what's giving us our various mineralogy here. But I guess the point I also want to make is we can tell not only texturally that propylitic alteration that's related to the vein versus the regional stuff, it's the mineralogy. The calcite comes in with the alteration that's related to the vein, whereas albite's related to the more propylitic stuff. The regional propylitic stuff there. So again, it's a combination of mapping your textures and understanding your mineralogy and what's going on in your system. And I won't belabor this point, but from all that work, I was able to put together sort of geochemical vectors in and around the Gosowong vein system. This was quite instrumental in helping people in this district and others. We did everything from looking at the initial SWIR data in through here, where we found the iron-rich chlorites were out here in the regional propylitic alteration, but they came more magnesium-rich as you moved into the deposit, and the chloride in the deposit was magnesium-rich. There was a very large oxygen isotope depletion as you moved into the system. I was also, you have your geochemical indicators up here at the surface, where you have elevated things like mercury, your precious metals, lead, moly, thallium, etc., and the alteration index, which is a way of using whole rock geochemistry to track into intensely altered rocks in either epithermal or VMS systems. The deposit proximal alteration here, what was added or taken out of the rock, the halo in through here up to about 50 meters, showing this zone in through here. And also we were able to track, because they had some deep drilling down into the footwall of fault, we were actually able to find the geochemical attributes of the structures that were actually the upflow zones. There was some quartz that was adularia that you could see was staining, but they also had distinctive things like potassium and thallium halos around it. High sulfur to sodium ratios as you're depleting things out of the rock, etc. So we were able to take different parts of the system, understand based on the mineralogy and the textures and the geochemistry, sort of indicators that the companies could use in the area when they were exploring. At the time, after Gosowong was discovered and was starting to be mined, Newcrest and the joint venture partners put in a camp, a mill, they were feeding it. They needed more, as things were going on towards 2000, they realized that they needed more mill feed. This time they started to reevaluate the Togorachi area where that boroporphyry was, because there was known epithermal veins there that were cutting the porphyry prospect. They went and started to reevaluate that area. Unfortunately, at this time in the history of the Halmahera and Molucca area, there was escalating sectarian violence and really, really bad violence at that time, horrible stuff going on. That limited the basically area that they could explore away from their exploration camp. Here, the bottom map down in here shows where the exploration camp is, right at the sort of discovery outcrop on the Quartz Creek here. They fanned out, that's a 2 kilometer and 5 kilometer radius circle out into the Togorachi area there. Before they were sort of chased off the land for a while, they discovered a series of these veins cross-cutting through the basalt and the diorite in that area. The Damar discovery trench is shown there, about 10 grams per ton gold. And then the Midas vein discovery, this outcrop they found in the jungle in that area there, it was 1.5 meters across, running 89 grams per ton gold. So again, these really, really high values in the Gosowong field are quite common. This brought them into the area. When they were able to get a drill in through there, they drilled what was called the Midas structure. The first drill hole on this section is the one I'm highlighting, red star, at 7 meters at 18 grams, and that got them very excited. They then did a lot more drilling, and you can look at the various grades on that. And what you will notice is the higher grades are all in this upper sort of 100-meter area down through here. The grades decrease in this part of the area down in through here. We're dealing 1 meter, sort of 1 gram down in here, a very small part down here. So we had the higher grades up near the surface. This is the pit where things have been taken out. And that's why they put the pits in at Togarachi, because they were mining these high-level quartz. But again, remember, it looks like you had an uplift of this basalt diorite package, epithermal veins put through it, and you've had this telescoping the epithermal veins onto the porphyry system. So these are some of the Togarachi pits in through here. The initial resource was only a little 0.4 million tons at near an ounce of gold. The plus 1 million ton resource there was when they went deeper back in about 2005 to 8 exploration and found deeper parts of the vein systems with some grade, and they went underground. When I was on the property, for the most part, I saw the open pit. This is the vein structure running down through here, the Damar vein structure running down in through here to the pit wall that's shown down in here on the drilling. The plan map here on the lower left shows the pink is the diorite, the dark green is the basalt. You can see these north-south structures cross-cutting through. These are very steep. They're not at that sort of 45 to 50 degree angle. They're very steep. The other thing to note in this diagram is this sort of black hashed line around and through here. That's a zone of 0.1 gram gold and 0.1% copper. That was an area that they outlined as this low grade or low tenor porphyry prospect in the area, but it's clear that they went in there to mine the veins, and that low grade material still sits there, but it does show that there were 2 mineralizing events going on in this part of the district. This is what some of the Togarachi mineralization looks like, quite spectacular stuff. Again, crustiform, cockade banding, quartz, chalcedony, beautiful bladed adularia is shown in here. You can see the blades going off. This is all around crustiform banding, around basically one fragment of the wall rock with crustiform banding on it. That's then being broken up and add a new set of sort of cockade banding or coming around the fragment in through here. So as with most of these veins, they're sort of compositional, they're polygenerational, multiple openings in the vein systems, multiple pulses of fluids coming in, and that adds to the increased prospectivity of these veins. The more time they open, the more times you get fluid into them, the greater chance you have for precipitation of the precious metals. And you can see that some of this material up in here, it doesn't look all that exciting, but it's 3 meters at 300 grams per ton of gold. That's good stuff. Daud Silatonga, that Indonesian geologist that was working on the property, also undertook a Master of Economic Geology thesis in the area, and he was tasked with pulling the geology of the Togarachi and Bora area together. And what he did was some really nice time slices down through the area here from the surface. You can see the red, in this case, is the intrusive diorite. The purple are the fault systems running down in through here, a series of these fault systems with splays and anastomos and portions to them, et cetera. And then what he did is you go down every 100 meters, the time slice sheet, you can see that the morphology of the diorite changes. As you go deeper and deeper down, you get down to almost like little plugs sort of were coming up and then blows out in areas like that. But also you can see as you move down within a couple of 100 meters of the surface, the epithermal veins basically pinch right out on that north-south lens. What we do tend to see is this thing called the T-fault, which is sort of almost an east-west structure in through here, having quartz-rich material on it doesn't really carry much in the way of grade. The real grade in the Togarachi area were these north-south veins down and through here. And you can see that when you're down about, say, 400 meters down below and through here, the veins have gone all together, and we do have sort of mostly basalt with small amounts of these plugs of the diorite coming through. So what Daud and Steve Micklethwaite did was put a very nice map together of the pit at the time. They could get into it before it completely filled up with water in 2006. I guess what's really important about this particular diagram is we always draw these things on maps as straight lines, right? Here's your vein system running through here. Okay, there's some big bifurcations and things in it, but they're that. But when you actually get in and map these things, they are incredibly complex systems. They have pinch zones, they have dilation zones, they have stepovers, they have linking structures, etc. So it's really important to understand the structure of these in an area. This is fortunate that in an open pit you can get in and see this sort of stuff. Underground is really important if you're trying to follow along it. Because if you figure, okay, you just got a drill hole there, a drill hole here, and a drill hole here, you draw a straight line through it. But if you just planned your mining just to go like that, through there, you would miss a lot of the material. So you have to have good structure control in these areas here. And you can see in the bottom on the pit, just those wireframes of the zones, and you can see why they put the pits where they were these little zones. And in fact, this little area here, this semi-parallel dilatant fault in through here carried grade, wasn't part of this structure, but it was part of a different structure in through here. Okay, well, that was the Gosowong Togarachi story. At the time that was happening, they mined out Gosowong, they were mining Togarachi, they needed to find more material to feed their mill. They basically came up, they knew they explored to the northeast and southwest of the Gosowong pit. They went back in there and re-explored it, looking for these shallow epithermal vein systems, where were the nice little pods within the structures, etc. Well, basically, they had no joy with the available surface prospecting techniques they were using at the time of the pit. Well, at that point, the hierarchy at Newcrest decided that they needed a new strategy. And that was based around the work they did at the Krakow epithermal field in Australia, in Queensland. These were deep epithermal vein systems. They had a lot of success with deep drilling, understanding the quartz textures, understanding where they were in the systems, and that led to a lot of increase in the reserves and resource in that Krakow area. So taking that combination of information, they brought that back to Gosowong. By that time, they'd had some new people move through the system, so they brought some new ideas in. So in November of 2002, they changed what they were doing. They were going to start looking for deep targets, not shallow. The added impetus for this was what I'm about to explain to you next, was Dan Olberg's 2001 prospectivity analysis. Now, Dan Olberg was a Newcrest geologist working on the property that I worked with when I did all my work around Gosowong. And he undertook this thesis, and this style of thesis is where you're an employee for a company, comes in and does short courses of codes, and at the same time does a project on an area they're working on. And Dan took apart this ore shoot targeting exercise down the whole Gosowong vein zone, not just the Gosowong deposit, the whole vein zone. And the idea was to find new high-grade ore shoots along the structure. This was thought to be the most structure in the district at the time, and the northern and southern extents of the fault zone hadn't really been explored or known that well. So this is the work Dan undertook. Now, this is the simplified geology map of the area at the time. You can see the Gosowong pit shown in that little zone in through there. This is the Gosowong fault structure in through here. This is the Togarachi area over here. This dotted line that I've just put on the diagram, that's the long section that Dan used through the Gosowong fault zone. Okay, so that's the starting point for how he put his prospectivity analysis together. Now, this is showing that zone from north to south. We've got the Gosowong pit shown in here with the two ore zones, the quartz adularia zone up here and the quartz chlorite zone in through here, and a little bit of stockwork zone with some grade down below. So this is the long section on that vein, sort of just on plan. But what also it shows is the piercement points all through here. This was all the drilling that had been done all up and down that Gosowong fault zone. After they discovered Gosowong, they went and drilled a lot of holes, but they didn't have a lot of success. So this was the geologic information Dan used. Now, this was information that was already in the logs, in the geochemical database, and anything else that had been done with consultant reports, etc. So he looked at the attributes of the piercement points through the Gosowong fault system, primarily geological and geochemical attributes. And what he did, and is shown here, the first thing we looked at was the stratigraphy. So here we've got in the Gosowong fault, in the pit, where we had the mudstones, the volcaniclastic sediments. There was a little what was interpreted as ignimbrite in through there, and that appeared to be the most viable stratigraphy. We had what was called the Depobo sandstone, which is a fine-grained andesitic rock. Down below, we had andesitic lavas up above, but it was where we had this combination of lithologies and the rheology and the fault system seemed to be where we had latent zones. And he wanted to know where else that had been found along the fault system. And you can see that that's that area there heading down towards the south. Then he looked at the total dilation, how wide the fault zone was and all these piercement points. And you can see that the greatest dilation was up in that quartz adularia zone, well over 16 meters at some points. Then it sort of got thinner as it moved down through the quartz chlorite zone and the stockwork zone there. But there was a couple of other big areas of blowout in through here. Here's an area here where we had 6 to 8 meters of fault zone in through here. And then this area down to the south, again, had zones up into the 10 to 12 meters through the Gosowong fault zone, but it hadn't really been followed any further at that point. So that was another piece of the puzzle. And they did know that the steeper portion had the greater dilation part to the system. Then he looked at the quartz textures. And again, the company itself had good luck of the Krakow area looking at quartz textures, etc. Basically, in the red is the crustiform, coliform banded or polycomposition, or what I call decoration in these systems, where you get multiple openings, multiple generations of fluids, you get banding, you get breccias, you get banding around breccia fragments, etc. That's the good stuff in this particular case here, and that's what we saw at Gosowong. The other interesting feature you want to see in that is the quartz after bladed calcite pseudomorphs. In that case, or quartz pseudomorphs after the bladed calcite, that indicates that boiling's gone on. The presence of adularia and the presence of the quartz after the bladed calcite, or the bladed calcite originally, indicates that boiling was going on. And we know in these systems that boiling is a very important mechanism for the precipitation of the precious metals. So in this particular case here, there was some deep zones down and through here that actually had the bladed calcite indicated, or pseudomorph, indicating that boiling may have been occurring in that zone. Then he looked at the alteration, and this was the very early days of the SWIR technology that people were sort of coming to grips with what we're finding. But what we found up on the pit, based on my mapping when they did this work in here, in the upper part, that quartz adularia zone, we had illite, smectite, chlorite, metachlorite, and calcite, indicating slightly lower temperatures for the alteration there. In the deeper parts of the pit in through here, where the quartz chlorite zone was, etc., that's where we had illite, chlorite, calcite, slightly higher temperature potential for that mineral assemblage in through there. And following that, again, things were all sort of heading down in this direction down and through here with a little bit out there. And that's also where we had a bit of a blowout in some of the dilatant zone in the vein. He also looked at fluid inclusions. This was based on material that had been done in some consultant reports, and Dan undertook some fluid inclusion work himself in this area. He found that basically between 2 and 250 degrees was the optimal temperature for where the mineralization was in the Gosowong vein system itself, and that's what we know from many of these systems worldwide. That's right in the money zone. Temperature range in through there. You can see the 2 to 250 zone is spread sort of across the property. It's only till you get down deeper down in here that things get probably a little too hot, and quite hot down here at 314, well deep down in the vein system here. But again, across this zone and through here, we're in the right temperature range. Then he looked at gold grade. It's always good to look at gold or the precious metals when you're trying to do a prospectivity analysis. This is showing the gold grades here, again, pointing out the two ore zones within the pit. But there were zones up in here where we had some nice indicators before, and also down in through here. There was things that hadn't really been followed up because after they initially found this, they ran over to Togarachi. But there was some indicators there was some gold down in this part of the system down in the south. Excuse me. And then we looked at a lot of metal zoning. They had a very nice assay database all through here. We looked at a lot of metal zoning. The idea here is you ratio an element that precipitates a lower temperature over one that precipitates a higher temperature, and you ratio those, and that can give you some idea of potential fluid flow directions or fluid pathways along the fault structure. And those purple arrows were some of the interpretation that Dan and I put together, trying to understand where fluid flow might be along the vein system. So basically, based on that, Dan put together this prospectivity analysis, and he's got all those various attributes shown in the red there on the left, and then he assigned values to them. So for instance, in the stratigraphy, Gosowong volcaniclastics, that was 10 points. If there was mudstone there, that was an additional 5 points. The other rock types got a 0. Now, I'm not going to go through all of these in detail. You can read those for yourself, but that was the process behind putting this together. What was the most important attribute? What was the good attribute? What didn't work at all? He assigned values to all these points. And what he used that material for was he took that entire fault zone, he divided it up into 50 by 50 meter blocks, overlaid everything on top of those attribute maps I just showed you, totaled up the values in each of those 50 by 50 meter blocks. And you can see that basically by using the Gosowong deposit as a training set up in here, these are the highest values, and you would certainly hope so, since that's what we're basing everything on. But there's a big swag of high values down here and some interesting ones up in that area there. But the most interesting part of this particular system was shown in the red, that whole area going down to the south. So based on this, Dan put together this sort of summary diagram with a prospectivity ranking, totaling things up and contouring it, showing that that area down deep into the south had some of the highest sort of rankings as compared to the Gosowong system itself. It wasn't the same as Gosowong, but it was high ranking down in through there. And he had C, D, and E as subsidiary targets to be it. Well, basically, based on the work on the ground, what they were doing, etc., Newcrest took this information on board with their other exploration they were doing at the time, and they decided that the most prospective area was, in fact, this area down to the south, off to the east. Remember, this is dipping off to the east down through there, and that's an area they would go down and start sticking some holes into to see what they could find. Well, this led to the discovery of the Kanchana deposit. In early 2003, a drill hole was targeted at the southern end of the Gosowong structure. Now, as fate would have it, where exactly they wanted to put the first drill hole, they couldn't really get into that area, so it was moved about 50 meters away from it. And they drilled, and they were heading down towards the Gosowong fault zone, but just before they got there in the hanging wall, they discovered a very high-grade epithermal vein. That first intersection was 7.25 meters at 29 grams per ton gold, including a meter at 140 grams per ton gold. Bingo, they knew they were onto something. The other interesting part was the Gosowong fault zone itself was intersected. It was 50 meters wide, and what they had known from the previous material, that it was going to be quite dilated down in that area, but only around half a gram. So if they'd only targeted that and didn't hit this hanging wall sort of fault system coming through, we might not be here talking about this right now, but they did. So good geological work, collecting of data, using that data brought them into the right area. Yes, there's a bit of serendipity involved, but they're a good exploration team, and they actually snagged onto what is now we know as the Kanchana vein system. In May of that year, they put out a press release basically announcing the discovery of this particular deposit. They found an envelope about 200 meters long, 100 meters down dip, and the thickness from 3 to 20 meters. You can see some of the grades of the drilling intersections reported there. I'm sure any of you that are working for companies, if you went into your boss or your board and said, I just hit 23 meters, 110 grams per ton of gold, you'd probably get a promotion. So yeah, these were the grades we were getting. An incredibly rich district. From some of the early drilling, this is what they sort of put the geology together with. They found there was both in the footwall and the hanging wall this quartz stockwork zone that we'd seen certainly at Gosowong with lower grade material. Then there was a shear right along sort of the hanging wall side of the vein. Then you got into the main ore zone itself, which had bonanza grades in it. This is where they could tell from the drilling it was multi-phase banding and breccias, etc. That sort of decoration of polycompositional material that we want to see in these zones here. But what you can see from this is the drilling. This is that came out of the ground. Drilling through these systems, you often do not get great core recovery, simply because of the nature of the textures and the material. This quartz-rich material, especially if it's got chloride or sericite or illite or something in it, breaks up quite dramatically. So you don't get the real picture of what's going on when you just see the core coming out. Of course, you get your assays, but you actually don't get to see generally the whole geological story through the vein. In hindsight, they went and looked around the surface a bit more, and what helped is they actually put a road down into Kanchana. It's an underground mine, as I'll show you in a minute. And what they found was an illite-rich zone in between these sort of weakly propylitically altered andesites. And this is thought to be the surface extension of the Gosowong zone. It's blind. It's down about 70 or 80 meters below this point. But it did have a bit of carbonated quartz veining in it. So in hindsight, it was, but I imagine if you were just walking on the surface, you can see at the top of that photo all the vegetation in the soil, you would probably walk right over this sort of set of weathering, etc. in this area. The jungle is what's shown on the bottom right. It is thick, temperate, or thick jungle rainforest. It is hot, sticky, wet, and full of bugs and snakes. When you do field work in this area, you're accompanied by a security officer with a very large gun. As you can see there in the bottom left, that's Dowd, Lindsay, and myself with our friend, the security guy that very faithfully traipsed around the field with us all day, keeping us safe, and we appreciated it. Lindsay undertook her PhD on Kanchana. The resource that was announced was 4.4 million tons at 27 or almost 28 grams per ton gold and a similar amount of silver for 4 million ounces. It's the big one to date in the district. This is showing sort of one of the cross sections through the deposit. Lindsay worked on a number of them, showing in the pink these sort of diorite, almost like sill-like bodies to dikes cutting through the system. We're dealing with feldspar ferric andesite. We're in the andesite member of the Gosowong formation there. There is some basalts in the package as well, but deeper down, and various other sort of volcaniclastic rocks, siltstone, sandstones, etc. in the area. There are some subsidiary faults through there. You can also see that the Gosowong vein system is broken into a series of little slices or zones where things have opened up, etc. along the structure, and I'll show you that in just a minute. The structure itself is shown here, a plan map in A, and then sort of an isometric diagram on the right-hand side there. There are two main sort of vein systems, K1 and K2 for Kanchana 1, Kanchana 2, and they're actually linked together by what's called the K-link structure in there in the purple on the right-hand diagram. Overall, this appears to be a northwest striking listric fault. The dips you can see are sort of moderate, much like Gosowong, normal fault movement from the indicators. The overall strike length is about 1.5 kilometers. Average thickness is 8 to 10 meters, but it does dilate to 30 in places underground. And the down dip extension from surface to the deepest part of the main system is about 370 meters, as we know it in the ground. They then had to go underground. They put a portal and a drift into the mine itself, and then did all of sort of the mining, as you can see in the red zones there, with some shafts put up for ventilation. This is what Kanchana looks like underground. It's a big, beautiful beast. Those are 1 meter red marks across the face. This is about a 7 or 8 meter face underground here. You can right away, you can see it's not just a simple quarrying. There's a number of different sections. You can pick different morphologies in through that. This is what Lindsay was tasked with, going underground and trying to sort out what the vein stratigraphy looks like. What are the controlling features? Where's the grade? What's going on? And she did do a great job. Before we go to that, I'll just show you what some of that sampling looks like across the vein. So this whole thing was 7 meters at 88 grams gold. But you can see some of the grades are quite spectacular in those 1 meter chip samples across those areas. And for instance, you can see this more massive quartz zone in through here is only running 11 grams, where these sort of breccias and things in through here, this is where a lot of the grade is. And then we get down into this zone, which doesn't seem to have as much quartz, but also brecciation, but then the grain drops as well. So it's not evenly distributed grade across the vein, and there are different textural styles through it. So what Lindsay did, from painstaking mapping and looking at photographs, they also did a fantastic job of photographing all their faces when they went through the mining. From ground truthing in the photograph, she was able to come up with these 11 different infill stages or types through the vein system. I'm not going to belabor this point too much, but good geological work has shown this. And why this is important, only stages 7, 8, and 9 carry the grade. Stages 1, which is the wall rock, through to 6, which is various amounts of quartz infill with some red chalcedony at times in through there. It has a little bit of grade in it, but it's not the bonanza grades. They come in 7, 8, and 9. 10 doesn't carry any grade. Interestingly enough, the very last stage to infill this vein system has molybdenite in it. We'll come back to that a little bit later. So what she did, these are just showing some examples of some of those textures. Now we've got examples of 7 and 8, 7 being the nice cockade banded quartz chlorite breccia grade, and then the 8 is the crustiform banded quartz chlorite. But different parts of the vein, you either have banding just on itself, clear open space, infill, or cockade banding around a breccia zone where fragments are blown into a dilational space. The fluids come through and form the same sort of banding, but around breccia fragments. Here, I show a couple of examples of 8 and 9 with the grade. Very, very high grades here. And the top example, we've got quartz chlorite banding in through here. The green is the chlorite quartz in through there. All this light-colored material here is electrum, pyrite, and chalcopyrite. There is chalcopyrite in this particular deposit. And type 9 down in here, we tend to lose the chlorite. We get more crystalline quartz with chalcedony, and again, very specific bands in this particular case, where we've got our pyrite, chalcopyrite, and electrum in through there. And often you will see that. You will get just certain points where, bam, all the gold drops out. It could be boiling, other features going on to cause that, but we do get these distinctive bands of really, really high grade in these systems. photo here, type 9 at the top, it also carries grade. That's one that also carries a lot of the adularia. That particular system there, or a particular sample, is one of the ones we actually age dated in the case there. And then finally, 11, all that blue to black material in that sample is actually molybdenite. And for those of you that know a fair bit about epithermal deposits, that's not a common mineral in these systems. This is showing the different mineralogy based on the different stages there, both the gangue minerals and the ore minerals. You can see the distribution of them there. I've highlighted the main orange stages in red through there. You can see that's for the electrum and the chalcopyrite. They tend to go hand in hand. We also tend to pick up some base metals, base metals, selenium-rich galena, for instance. You do get other sulfides down in through there. And then you get into a myriad of sulfosalts, tellurides, and selenides. There's a number of selenides in this particular deposit too. And then finally in the green, we've got our interesting feature with the molybdenite. It still carries gold. It still has the galena and stuff in with it and some of the other sulfides and sulfosalts, but importantly, it also carries molybdenite. So from all that work, what Lindsay was able to do was put face maps together showing the distribution of these various stages. And what we found was a huge amounts of brecciation. Basically, you would find early stages caught up in later stages and fragments, etc. And they rebroken and rebrecciated. So this vein system had a very long history of opening fluid influx, to create banding and breccias through it. So what she did from the face maps, she turned into these strip maps. She then plotted those strip maps on sort of a long section through the vein. This is K1, just the K1 load here, and showing the distribution of that. And staring at that, you just see a multitude of colors, but the next diagram will show you how we sort of sorted this out. You can also see that the system's blind in this particular section. We're 70 meters from the surface, and there's no indication at that point. In this section, there's this much gold or silver just down below. So we do know that we want to see where the distribution of stages 7, 8, and 9 for the gold and 11 for the molybdenite. Well, it turns out they're primarily developed from the north to the south through the vein system. So it appears that we've had fluid flow down the Gosowong Fault or subsidiary structures in the area from the northern part of the district into the southern part of the district. We saw that I didn't explain it to you, but the same thing happened in the Gosowong system. We saw what was going on there. So you can see that green zone is where the molybdenite is. The fluid source is thought to be deep from the north. We've got our blue zones where the gold is. And then as you move to the other parts of the area there, the grade is still there. There's not as well developed the blue zones, the ore zones, and through that you get a lot of the earlier stages infill in the vein system. And this is what happens in epithermal vein systems. These open, they don't open evenly or consistently all across their structures. You get pinch zones, you get dilatant zones, you get your orange zones or orange shoots within your structures. And that's what these sort of diagrams are showing us. If you look at the metal zoning, you can see in the sort of the upper parts of the deposit, that's where we're getting a lot of our gold and silver. The base metals are distributed through there, the deep fluid source to the north. If you look at that diagram, the inset box, you can see we've got this sort of copper moly lead zone coming in from the north and the deeper parts of the system. And then we move in through our gold-rich zones into our zones further down to the south, where we're sort of losing a lot of the grade, but we're picking up our sulfosalts, probably indicating slightly lower temperatures, or at least not as well developed ore zones. This is the camp, very, very comfortable camp to live and work in. But what I'm highlighting here is the mill complex. That's sort of the bottom left photo there, and you can see the various features that go through the mill. I'm not a metallurgist, so I won't go through it. But what I will show you is the diagram on the lower right. This is where the real high grade goes. This is 8 people that hand sort the ore. Basically, they're trained to pick stages 7, 8, and 9 compared to the other ones. And they actually hand sort that ore, and they blend the really, really high grade material with the lower grade material into the mill to get hopefully a more constant mill feed, and they don't lose a lot of the precious metals. So the only other place that I've seen this sort of style going on was Hishikari in Japan. I'm sure there's many others there. The only one I've seen is Hishikari, and there that was direct shipping ore. They just separated the really high grade from basically the wall rock from the ore zones and direct ship that out to the smelters. In this case, they separated the really high grade to blend into the mill. So this brings us to the last sort of bits of the talk now. But we're now going to talk about these porphyry prospects, right? We've talked about the really good stuff, the epithermal system, but now we're going to look at the porphyry copper gold system. They're sub-economic, but they're very, very interesting. There's a number of them there. Bora is the one where the Togarachi veins are, Tobobo, and the other ones are other examples. Remember, the age dating for the alteration is 3.5. They're older than the epithermal veins, and again, you see that same pit map in the Togarachi pits of the epithermal veins superimposed on top of the magnetite biotite alteration of the porphyry system. This is where Michael Dunn, the honor student, comes in. He looked at a lot of the sort of prospectivity for the porphyry systems, but again, using it from a geophysical point of view. This is his map of the area. You can see the red stars of Gosowong, Kanchana, and Togarachi in a relatively small area down through there. What's highlighted in the sort of gray dashed lines are the zones of known sort of porphyry style mineralization or alteration in the district, going from Bora up to Alannah, up to the north. There's another little epithermal system, Batuapi, up in there in the west as well, but we're highlighting sort of where the porphyry systems are. And you can see, interestingly enough, they look like they're on a slightly northeast trend up through that particular map. The little photo inset is some core from the porphyry mineralization down at Bora. Down through there, that's high temperature potassic alteration of the diorite in the background. That's basically biotite and magnetite alteration with a bit of actinolite there. That's then cross-cut by sulfide-bearing and quartz-bearing veins in through there with an alteration halo of more argillic or sericitic alteration, I should say, superimposed or overprinting the potassic alteration. Quite common features you tend to see in porphyry systems. So these porphyry prospects are shown here. We've got primarily quartz magnetite, plus or minus some of the copper minerals, chalcopyrite, boronite, pyrite, stockworks, and these altered diorites. You can see some of the grades there. That's sort of 0.1, 0.1. Interesting systems developed there, but wasn't really particularly juicy. The early potassic alteration we discussed, and then we've got it overprinted by the sphilic or SEC alteration, and later sort of clay carbonate alteration as well. The diagram on the left is some of that stockwork veining in the open pit at Bora, and the Togarachi pits in through there. You can see the nice stockwork veining cross-cutting through the diorite. The beautiful photo on the on the right is a classic example of, in this case here, the stockwork veining in the altered diorite that has been broken up as a fragment in the Togarachi vein systems. And you see beautiful cockade banding coming around with quartz and adularia, and then other sort of chlorite coming in, and that actually carries a fair amount of grade. But again, showing the superposition of the epithermal on top of the sort of porphyry prospects. Michael Dunn undertook looked at the magnetics across the district and did some regional inversions, as shown in through here. Again, this is the map showing that sort of northeast trend of these potential porphyry prospects in through here, coming up into this northern area here. B, this diagram here, is the gray surfaces are basically mapping out the magnetic intensity of a body at depth with, it's a little hard to see, but there's actually apophyses coming off a deep body at depth up into right under where the Bora, Tobobo, and those other porphyry prospects are. So they seem to be basically from that deep zone funneled up apophyses. The fluids have come up those apophyses of the diorite, and that's where we're getting that porphyry style alteration. There's, interestingly enough, another zone of over here on the right-hand side of this diagram where those apophyses are coming up towards the surface. He's highlighted these areas here, but nobody had found any porphyry mineralization to date or alteration that I know of in that area there. This is a very large zone of near surface magnetization down here, down into the south as well. If you look at sort of that inversion model sliced through here, you can see we've got this larger body at depth, highly magnetic, and then we've got these sort of apophyses that are coming off it, and they come up into the zones where that porphyry mineralization is. So, nice example. We don't know if there's something bigger or better down there that hasn't really been explored, but the new company that's taken over in the area may put some time and effort into looking for potential porphyry. And the last piece of the puzzle is a lithocap. It does turn out to be a large advanced argillic lithocap in the northern part of the contract of work in here. Here's the Gosowong vein. This is quite an old map, I admit, but it's the best one I have that shows the lithocap. Here's the Bora porphyry. There's Tobobo. These are some of those other ones coming up that northeast trend in through here. But this is this large lithocap up in here. Excuse me. It's got areas of vuggy quartz. In it, it's also got alunite, porphyroid, diaspore, dicite, and kaolinite, all the classic hypogene advanced argillic alteration phases. Now, remember, when I told you very early on in this talk, this is where this material has been dated at 2.8 to 2.9 million years. So this lithocap is actually the same age as the epithermal mineralization, but appears to be much younger than the porphyry alteration, at least is dated down in through here. That doesn't mean that maybe there's another intrusive phase or something under here coming up, but who knows what that's actually covering over. So it's a very large area here that may be hiding all sorts of goodies up here in the district. So we've come basically to the conclusion of the talk now. All right. So basically the Gosowong Goldfield has tremendous epithermal deposits in it, some of the highest grade ones that have been discovered in the last 20 or 30 years, and through here, northwest structures through the area, exceedingly high gold grades. Newcrest and their joint venture partners have made a lot of money out of this particular area. But I guess the other thing I want to highlight, especially for some of the students out there and some of the people working for the companies, is I'm a big believer in using data you've got to get more out of it. The Gosowong fault zone prospectivity analysis was using data that had been collected with good sampling, good core logging, etc., using that in a prospectivity analysis on the fault zone, looking at all the different attributes that pointed them into an area that had a lot of the right attributes, and from that, this helped them find a very major gold-rich ore deposit. The district has over 6 million ounces of gold at an average grade of about 30 grams per ton. Really, really high-grade stuff. It's a world-class epithermal district. A lot of people have heard a lot about it, something which is very hard to get to, and it's been difficult to get to over the years because of some of the violence in the area. But I hope you've learned something about the Gosowong Goldfield, the epithermal systems, the potential for the porphyry, some of the alteration story, etc. Just to let you know that as I mentioned earlier, I am a consultant right now. If anybody needs any help with epithermal systems or VMS systems, I work in that space. Information's there, or you can find me on LinkedIn if you'd like to get in touch with me. With that, thank you very much.
Thanks very much, Bruce. That was fantastic. It was a really interesting and I think invaluable summary of this exploration strategy and the details of that deposit. I'm really looking forward to people being able to watch that. And thanks everyone else for joining us today as well. So really enjoyed it. Thanks, Bruce.
My pleasure. It's been a fascinating place to work, and there's been a lot of great geologists working in that area, the Indonesians and the expat at the same time. They're a really, really good group of Indonesian geologists there.
Yeah, awesome. I hope some of them were able to join us today. So
I might see some familiar faces out there yet. You never know.
Okay, so I'm just going to briefly go over how the discussion works and then we'll get into it. So I posted it up earlier in the chat, but basically there's a few ways to ask questions today. For those of you who haven't joined us before, you have 3 options. You can type a simplified version of your question in the chat, and then we will come to you, say your name, and then you can unmute yourself and ask Bruce directly. Then the second option is that you can type host and your question, and then myself or Chris will come to you and we'll read out your question for you to Bruce. And then the third option is if you'd like to remain anonymous for any reason, or particularly because this is being shown on YouTube, you can type anon and send your question to Chris or I, and we will convey your question for you. So yeah, we have already quite a few questions come through on the chat and also on YouTube. So Chris, I'll go over to you for bringing us a first question.
Yeah, we got heaps already lined up, so this is good. Usually I try to rustle up the first question. So the first one we had, which came from YouTube, is was there any geobotanical indicators for some of these deposits? So was any of the wildlife doing something different that was growing on top of these deposits?
I'm not a biologist. I can tell you they're a botanist. I honestly don't know that. I've never heard that. And all the papers that have been written about the discovery of the 3 deposits in the area, I do not know of any geobotanical indicators. I do not know of any strange behavior of snakes or the bugs or anything like that, or the mosquitoes in the area. So As far as I don't know, I never heard anybody talk about it. But on the other hand, I don't know if anybody's actually looked.
Yeah, I know it's not the most common thing for gold deposits. I know that much, but I know somewhere in that part of the world,
zinc moss and that sort of thing.
Yeah, there's that tree that grows grows on copper deposits, and it has like a blue-green sap when you hit it open, which is pretty awesome. Yeah. All right, who's next, Alannah? Who do we have next?
Okay, so I think we'll next go to Henry Tabar. If you'd like to unmute yourself, you can now ask your question. Hopefully
I think we can. We asked him to unmute, so I just asked him then.
Okay.
So Henry, if you're there, go ahead.
Yeah, it's really very interesting talk, Bruce. It's quite interesting to see that you got porphyry, you got the epithermal, is it low sulfidation and high sulfidation? How does the three types connect? I know that you put in the age of the porphyry is older, but and then you get the source coming from the south, I think, coming in. Is there a story here, one mineralizing source that fit everything?
Look, that's a very good, insightful question. It's work that's a lot of work's been done in the district to try to understand this. It looks like this big diorite body. Initially, when it was intruded into the package, it did have some fluids coming off it to form the subeconomic porphyry style alteration, a little bit of veining, etc. The chances are this has been a multi sort of generational diorite body. It hasn't really been mapped out that way because there hasn't been enough drilling into it. It's interesting. It's only 500,000 years later that the epithermal veins have cross-cut through it. But the other time, you think that whole area has been uplifted and the epithermal veins have cross-cut through it. So we've got amazing tectonics going on here that are lifting up. There may be, in fact, as that lifting up is going on, there may have been more magmas coming in underneath that has acted as a heat engine for the circulation of the fluids that are forming the epithermal veins. What we don't know is to the north, under that great big lithocap, that's clearly, this is a high advanced argillic lithocap, that's related to some sort of intrusive body down below it if the age dating is right, at the same time as the epithermal vein systems. So in May, in fact, we may be looking at sort of a zone district where you've got intrusions, you've got degassing up to a lithocap here. There may be deeper intrusions in that area. And I suspect if the structural architecture is right, there may be more of these epithermal veins, either hidden by the lithocap or around the edges of those intrusive bodies where you get into the right temperature regime. But to that northern part of the area, it's very mountainous. It's very hard exploration. You do have a lithocap there. I know Newcrest and their joint venture partners were spending a lot of time looking in there, but to the best of my knowledge, they haven't had a great deal of success. There are a few high sulfidation zones, weak mineralization that have been hit, but I'm not sure if anybody's drilled some really deep holes down there to test a potential porphyry system at depth.
Thanks, Bruce. Last question, Bruce. In terms of the vegetation cover, which is quite difficult, how hard is land access from the point of view of people issues, safety issues?
Look, I cannot tell you about right now because I haven't been on the property for about 6 or 7 years. When we worked there, basically when you went out in the field or went in even into the core area, I had to have a small bag with me that had all my prized possessions in it, because if something turned sour, the people on the ground that worked, the employees were the first ones up in the helicopter. It was actually fairly dangerous because of the ones in the island. The workers on the site were great, but you just didn't know if the area potentially could get overrun. That was back in the early 2000s. I believe that's calmed down significantly now. I've never heard in the last little while that there's been real issues, but I must admit I haven't kept up with what is actually happening on the ground. There may be other people in the audience that have a far better idea of that to help to answer that question than I could.
Wow, thanks, Bruce.
Okay, thanks very much, Bruce. We've got plenty of questions coming in here, so I'll go to the next one, and that is Marshall Adingra. If you'd like to unmute yourself, you could ask your question. Hopefully that works. Just give him another moment.
No problem.
Hi, Marshall, are you there?
Hi, Alannah.
Hi, great. We can hear you.
Hello, Marshall.
Hi, Bruce. Yes, many thanks for your presentation. It's very good, great talks. So you show a lot of texture of quartz. So I want to know if you find the links between the high grade gold that you find and the crystalliform texture quartz that you get. So did you know why the high grade gold is linked to this texture?
Okay, look, that's a good question. What we seem to think, it's not only just the texture, but it's clearly the chemistry of the fluid in that package that's come into these systems. It seems that, at least in the deeper, hotter parts of the system, getting the chlorite with it seems to be a really important indicator in these systems. It's the quartz, the chalcedony, the bladed textures, and deeper down it's the chlorite that comes into it. And we've seen that in a number of deposits around the world, that you get this banded chlorite in with the quartz. At the same time, sometimes you get some adularia, but that's generally slightly higher up in the system and through there. What we do know is where it's really distinctive banded quartz chlorite, we get the very high grade, especially in the deeper parts of Gosowong and throughout most of Kanchana, where you get banding that is quartz adularia in the higher part of Gosowong. That's where you're getting your higher grades too. I suspect it might be due to probably the onset of boiling in these stages, basically causing a rapid drop of gold from the solutions. You've had boiling, you created alkalinity changes in the fluid, you had adularias coming in, your gold is precipitating out, etc. So I think we've got that. Where you see, often in these systems, where you see what I call decoration, the multiple generations of banding, crustiform, and coccate banding, etc., you often get a lot of grade in those areas. In the Japanese case, you have the jinkuro bands, those thin little bands, and quite often that's all you get in these systems. You get thin little bands where most of the ore minerals are in quite a large system, simply because all the physiochemical conditions for the fluid, its temperature, its composition, everything else is right, and it drops the precious metals out almost instantaneously out of these fluids. So those are the sort of features I always look for when I'm looking at these. If I just see full quartz, for lack of a better term, just massive crystalline quartz, chances of having grade is not very good. On the other hand, if all you see is chalcedony, you're probably too low a temperature, and you're not likely to get much grade in that rock too. It's that in-between period where you're getting a combination of some crystalline quartz, chalcedony, adularia, in these particular cases, chlorite. Other systems, it could be carbon. These particular ones, it happens to be the chlorite.
Okay, thank you.
Excellent.
All right, we have one that came through from YouTube. It's why do epithermal deposits always have manifest themselves with narrow alteration, and why are they narrow in general?
Okay, quite often what happens in these cases here, as the systems open up, you tend to get precipitation from the wall rocks in. So depending on how the fluids are actually getting through the vein system, through the previously formed parts of the vein out into the wall rock, you're basically, you don't get much fluid flow going out there. You may not get a lot of alteration. The other feature to remember is these are high level systems. So the rocks are relatively cold when the fractures are going through. So the fluids, it's a alteration's disequilibrium, right? You've got a hot fluid coming off a fracture, hitting cold rock. As it cools against that cold rock, it's buffering against that rock, you actually end up with relatively thin veins. If you get deeper down and the rock package is hotter, your alteration can actually extend out further because it's not cooling down. And as it doesn't cool down, it has more chances of altering the rock and changing the mineralogy. In these vein systems, quite often, the alteration is not manifest itself very far. I've got a student now, and I've done my work down in Mexico, where it's mostly in sediments. The alteration, visual alteration, could just be centimeters wide around a vein. In this particular case, in the Gosowong systems, they're up to, some of the features are up to, say, 50 meters with the epidode veining, but most of the alterations confined to only several meters right around the vein system itself.
Do you reckon, I'm just going to tack onto that one, do you reckon it has to do with the overburden pressure as well? Like where they're quite shallow, you don't have enough confining pressure to allow fluids to kind of seep out on the wall rocks, where they'll fracture a lot easier without having the overburden?
Well, there's a couple of things there. One, if you think of these fractures going up to the surface, right? You change from lithostatic pressure to hydrostatic pressure in the conduit. What we do tend to know is these things go up to the surface, they tend to flare out. So you actually get funnel-shaped alteration systems. Often near the surface, you can up near potentially where the water table was or where you may get your steam-heated alteration. We often see the alteration flaring out through fractures and fluids interacting as it goes up. And then it gets more tightly confined as you get deeper down in the systems. We're relatively deep in these systems. I think these systems are somewhat deepish, and that's why they're relatively tightly confined into the structures themselves.
All right. Who's next, Alannah? Who do we got?
Okay, so we have one question coming in here from, I'm sorry if I pronounced your name wrong, but Guista Sampurno.
Giesta Sampurno.
Sorry about that. But if you'd like to unmute yourself, you can ask your question.
Hi, can you hear me?
Very well.
Yes.
Okay.
Hi there.
Hi, Bruce. Me, Ista from Indonesia. I would like to ask about in district, Gosowong district. You mentioned at the end of the presentation that you have the area has a quite huge lithocap area.
Yep.
My question is it mineralized? I mean, is it potential as a high sulfidation deposits? And you also mentioned that might be related to a different age of the porphyry system compared to the Gosowong system itself. And my question is, the first one is that one. The second one is, do you think if there's any high sulfidation of the same as the porphyry system related with the Gosowong, is the high sulfidation is already eroded or is it not developed? What do you think about that?
Okay, and I'll answer the second one first. About 50 slides back, if you remember a cross section of the Gosowong vein system, there was a little area at the very top of that had vuggy quartz in it. Mm-hmm. It seems that in this particular district, and this is work that an honor student did at CODES back about 2013, they actually found that it looks like in some of these vein structures may have been opened up. Again, we've actually had advanced argillic and or high sulfidation mineralization going up those fault structures. When you think about it, what was the very last stage at Kenchana? It was molybdenite, which may have a somatic source or an intrusive related source in that case there. So yes, in the district, it has been recognized in a couple of places where there is high sulfidation mineralogy being found in some of these vein systems. It wasn't actually known at the time what they might be related to. We do have down near the Gosowong area remnants of what may have been a lithocap, but we don't know if that's been superimposed on some point later on, but it looks like it's come up part of the Gosowong fault structure in that area. The big lithocap to the north could very well be hiding something juicy down below it. I do know that the group was working on exploring through that area. Because I moved on to other projects, I didn't really keep up with what was going on there, so I don't know if there was any deeper drilling, following targets, trying to find root systems to the advanced argillic alteration, which may lead into high sulfidation systems there. There may be somebody in the audience that, again, knows the more recent history of the field than I do. But look, from the geology we've seen, the features that are going on, the potential of that lithocap, or at least under that lithocap, I would think is high. What you want to do is kind of find the structural roots where the fluids are coming up. That's where you may find some sort of vein-related high sulfidation mineralogy, or if the stratigraphy is right, there may be lateral sort of replacement of the rocks and the high sulfidation mineralization in through there. So yes, I mean, to me, it's always been incredibly intriguing that this big lithocap now is, when we recognized that it was sitting up there, I didn't recognize it, the geologist did, but what was actually lurking underneath it, and I don't know the answer to that question.
Okay, thanks a lot, Pat.
Wherever Giosta was sounds beautiful, and I wish I was there. So we have two questions going to tie together. Both the people who asked are gone, but they're somewhat similar. So Extivenus Franciscus, I think, has asked, how about a geophysics anomaly signature within the project area, especially with respect to the low sulfidation epithermal system? And Robin Arman asked if anyone's tried using geophysical techniques to look through lithocaps.
All right, I'll go with the first one first. They did do a lot of geophysics through the area. There's airborne mag that's been flown, gravity. They've been on the ground with mag. They've used CSAMT, they've used IP, etc. None of those have led directly to a deposit discovery. They have been useful in helping pick different parts of the geology or structures apart, but none of them have led directly to an ore deposit discovery, to the best of my knowledge. The CSAMT was useful in actually picking the basaltic member from the andesitic member of that Gosowong rock package, and to see across faults where the offset is being, et cetera, along those lines there. The regional alteration, or the regional mag, I should say, actually, that was some of the work Michael Dunn did. That helped pick some of those. He used it from the modeling to pick the apophyses. That magnetite alteration shows up quite strongly. He could see the apophyses down below parts of that lithocap. He didn't extend it all the way to the north, but to the best of my knowledge, that geophysics, again, in my part of the time in the field, didn't pick out any targets that were drilled. But like I said, I haven't been on the field for about 6 years or so. So they may have had some joy there. I just haven't heard about it.
All right.
Okay, we've got another one here for you, Bruce. So one for me to read out. Is the behavior of the gold-bearing structure, or what is the behavior of the gold-bearing structure at greater depth? Do you think it disappears, or is there something that may be still undiscovered even deeper down? And do the gold grades change, or how do they change there?
Right. Okay. What we know from the metal zoning is in the Gosowong fault system itself, what it tends to do is it tends to shallow with depth. Where it's been drilled into, et cetera, the thing, sort of like a listric fault, it's actually been shallowing with depth, and the gold grade dramatically decreases. It seems to get hotter from the quartz textures and the fluid inclusion. So we're out of that epithermal window for gold deposition, but it does seem to shallow as it goes down in through there. Kanchana seems to do the same thing. Togarachi are vertical veins, but again, from the gold grades and stuff that I showed in a couple of diagrams, they decrease quite dramatically as you go down in that area there. So, and what we did know, at least when I was working right around the Gosowong deposit itself, is there's a number of these kind of listric faults coming up in the area, and we were able to use geochemistry to pick what we interpreted to be the fertile faults at depth. And that was something that they were following along, that they've hit some of these things in some of the other holes, and then follow up sort of dip from those points if they hit them in deep down to see if there was a structure that dilated higher up in the system. Basically, apart from that, could there be something deeper? But the other point is, remember, there was an awful lot of faulting in this district, and it depends whether you've got blocks of rock that are being dropped down. And if you're in that sort of epithermal window of 200 to 250 degrees that was there, and then faulting's dropped it down, yes, there would be potential down in through there if that's where the geology or the fault's being dropped down and sort of younger faulting. So there's always that aspect of the story. I don't think, from what I've seen in the district and everything so far, that if you followed, say, the Gosowong fault system down or even the Kanchana fault system down, you would get any more deeper down, from my understanding, simply because you're getting deeper, thinner, and hotter. And you had to get up into that zone where the temperatures were right, the dilation was right, and that's where your mineralization is.
That's great, thanks. Do you have another one there, Chris?
Yep. Oh, we got heaps. If you get tired, let us know, Bruce.
It's all right. I'll have to go open a bottle of wine here in a minute.
Yeah, I already got a beer cracked. This is an awesome question. This one's from Marcus Stobin, I think is how it's pronounced. First of all, he says thank you, which is always nice.
I'm pretty sure he was one of our graduates.
Oh, really? Well, maybe it's loaded.
Hi, Marcus.
Does
He's on
the
YouTube.
Gosowong epithermal and smaller porphyry prospects correlate to any larger downgoing slab anomalies on a large scale? For example, the Ru Rise or the Batu Hai Zhao?
Oh, Beta-Hijau and stuff like that.
Yeah.
All right. Let me.
Dust off your tectonic hat.
Yeah, I was going to go back. Yeah, well, I'm not. I'll potentially get through this, but we'll go back and look at that. Good question, Marcus. There. Look, this is a really complicated area. One thing that's kind of interesting is this area here. You've got these ophiolitic chunks of ocean crust that are coming up and blocking into where you've got subduction going down, you've got your arc being formed in through here, etc. The Backhand Island, there's a small porphyry system situated right down in through there. But a lot of this is sort of high level stuff in through here. I think the areas for the big porphyry systems could be sort of potentially back in this area and deeper down in through here. Your question, Marcus, about what's going on deeper in the slab, I don't know. I do know there's incredibly shallow seismicity all in through here, and then the seismicity does show it gets deeper down out in through this area and certainly down in through that area. So that's the subduction zone sort of behaving its way down in through there. What's actually happening with slab melting at depth, I don't know. I'm not an igneous petrologist and sort of work in that field. I'm more the deposit related scale and things of that nature, but it is interesting. Here's Grasberg's is situated right about in there, in area, that sort of area down in through there. We know we got gold deposits over in here, Tokatingdung and some of the other ones in that area there. We do have some small porphyry prospect there and there, but as far as I know, it's down, Backhand Island's down in there. I haven't seen any indication in this area that there's any other big sort of porphyry related systems going on these really quite young rocks.
Really interesting. I hope that satisfies Marcus. He's asking from YouTube, so sorry he can't.
Oh, okay, fair enough.
But that's excellent. Okay, so we've got still quite a few more questions. Maybe we'll go for 5 minutes more, and then.
Sure.
Yeah, don't want to take your whole evening. So
it's all right. Dinner will wait.
Okay, so we've got another one here from Brian. Brian, if you'd like to unmute yourself, you can go ahead and ask your question. We'll just give him a moment.
Yeah, I just asked to unmute you, Brian. It should be near the bottom left of your screen. There'll be a picture of, there you go.
Hi, Brian.
We can't hear him.
Yeah, that's sorry about that, Brian. We can't seem to hear you.
Would you like me to ask it on your behalf? Because you have it typed out. I can ask it for you if you like.
Yeah, I think in the interest of time, let's go for it, Chris. You can read it out.
Okay.
Sorry,
in underground mines, how are the faces sampled? Were they channel samples or panel samples? Also, Kanchenka looks like a classic bridge structure. And he apologizes that his mic isn't working.
Yes, as far as I know, it was classic channel sampling when I saw the people working underground. And yes, it does look like a potentially a bridge structure into that area. It is a series of two veins with link systems through it, is the best of our understanding through it, yes.
Okay, great. Thanks, Brian, for that question. Chris, who are we going to next?
Yeah, I think we actually have 2 more questions, and then we might be off the hook. And I have a little question myself I might put at the end if you're up for it. But first, we'll go with our audience. What about tellurium? Is there tellurium, and has it been used in exploration?
Yes, there are tellurides in these deposits. The indicators on surface, tellurium didn't seem, at least from what I've seen of the soil geochemistry, hasn't worked that well. Other things have worked well. Tellurium is there in the tellurides. There's selenides, there are tellurides, very minor quantities. I mean, there was a point of saying, yes, they're there, but as you know, it's the sum total the size of your thumbnail in the deposit. It's a little bit bigger than that. Tellurium didn't really seem to show up that well in the weathered profiles that when I saw the soil geochemistry data.
All right. Here's one from Conrado. Is there any hot spring occurrences at the surface still?
No, not right in the immediate area where the vein systems are. There are others to the north on Halmahera Island. When you fly off in the helicopter, you do see steaming ground coming through. So there is actually modern hot spring activity on the northern part of Halmahera Island that I've seen, at least from the helicopter, not on the ground.
All right. Alannah, do you have another one that you said?
Yeah, we've got Ali Sholia, if you'd like to ask a question.
Ali.
Yeah, if you're still there, Ali, please unmute yourself. We'd love to hear from you.
I think we have to invite to unmute. It's Ali Soleh?
Yeah.
All right. I'm sending through the invitation to unmute right now.
Yeah. Good day, Bruce.
Ali, how are you? Good to see you, my man.
Great. Thank you for your great presentation. I'm very good, and I'm very happy to see you here again. Safe. That's good.
You too.
Bruce, I have a question about the length of alteration and mineralization. You mentioned 500,000 years difference between porphyry and epithermal mineralization, but I don't know if you have done any research or any guess on the length of porphyry mineralization and epithermal mineralization there, because sometimes porphyry mineralization takes.
Oh, you mean sort of the duration of the mineralized events?
Yes.
No, we haven't. To the best of my knowledge, nobody's looked into that. There's just been a few samples that have been grabbed and age dated. Nobody's, and it all depends on the mineralogy of the system. If you look at Kinshana, for instance, there may be 11 different stages in it, but all the first 6 are all variations on quartz. Then we get a bit of adularian with the gold, and that's we've age dated. We did try to date the molybdenite, that last stage. Molybdenite in it, but it turned out the molybdenite was too fine grained to be dated. We tried, we sent it off to all the right people, but they just couldn't get a reliable date. So the simple answer is we do not know the duration of these events. To be perfectly honest, I think these epithermal systems are short-lived. I don't think they're tens of thousands of years, something nature up to, maybe up to 100,000, but not more than that. I don't think you'll have structural architecture maintain these active tectonic volcanic environments, nor do I think you necessarily have your fluid flow system in operation for much, much longer than that. Wherever the reservoir of the fluid is, structures will change and may get shifted off somewhere else, not necessarily up the same structure all the time. I mean, if you look at sort of earthquake swarms around the world, essentially the latest Christchurch one a few years ago, things are going pop, 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 pop when fault systems are really, and and each one of those things may in fact open up, jiggle the fault system or break something, and fluids are getting into it through that. So I think these systems are actually fairly rapid, geologically fairly rapid. But to answer your question right off the bat, no, we haven't done a detailed study that at least I know my group didn't do it across the vein system to try to determine if 14,000 years or 84,000 years, something like that. We just don't know.
Thank you for the answer.
Good to see you.
Nice to see you too.
Thanks, Ali. Okay, I think we've got one more here in the chat. Chris, you're gonna go for that one?
I can't actually ask unmute this individual. He might not just have a microphone. So I'll ask on their behalf. This one comes from Nagona. What can be the provision of these areas in 10 years in the future, conserving the gold, and what is the method used?
Sorry, could you repeat that again?
Yeah, it's what can be the provision of these areas in 10 years into the future, conserving the gold, and what is the method used? I think it might have something to do with what's the method used to extract the gold.
Well, the milling in that, it's crushing, milling, and then cyanide.
Right, cyanide leaching, yeah.
Yeah, that's it. And that's where they had that's where the main part goes into the mill, but then they also separate some of that super high grade out to blend in with the lower grade material to get better sort of consistent mill feed. Because if you put a huge slug of really high grade in, you potentially have a chance of losing a bit of, or a chunk of it. So that's why they blend the high grade with the lesser grades to try to get a better mill feed. Because the mills are designed at a certain sort of throughput, mineralogy, grades, et cetera, for optimal sort of recovery. And if you overflow the system, you can have problems.
I am sorry if I botched that question. It was a bit broken.
No.
I tried. So I think we're done with the questions. I'm going to throw in one little one. I'm going to bring up our shared Canadian scar from the 90s. It seems like the exploration that happened in some of these areas was in the mid-90s when the whole Briec scandal happened, and it's definitely in the same part of the world. When you look into this and when you were working there, did you find that the Briec scandal, because it started in 93, I think you said the exploration here was around 95 or so. So did you find that there was a big push to explore this part of the world because Briec was ramping up? And then when Briec got basically outed as a scandal, did you find a lot of people pulling out? What was it like working there during the Briec time?
Yeah, no, look, I've got a couple of sides to that story. No, I didn't. I mean, you have to appreciate that back at that time in the 80s and 90s, we'd come through the porphyry model and how well that worked in exploration. Then we had, the Buchanan model in the epithermal world and how well that worked. This was also an area that had no real sort of, Western mining companies go through it at all. This was kind of almost virgin territory. There'd been a few groups go through and do a soil sampling. Remember, the very first group that went through there didn't even assay for gold, because back in the 70s, gold wasn't worth what it is today, right? They were looking for copper. Remember, Grasberg had been bound by then. I can't exactly remember when Badajoz was, but people were looking at the big, the porphyry systems through the area and looking at the young rocks, the intrusives, the porphyries. So that's why they sort of got into this area in the first place. On Kalimantan, I actually had a student, Andrew Davies, work at Kalian. And his very first thesis project was supposedly going to be Busang. And luckily, he never got started on it and shifted to the Kalian deposit on there. But look, I think people realized right away that was a unique set of circumstances led to that whole story. Okay. And it's not every mining company operates that way, et cetera, et cetera, et cetera.
Yeah.
So when I got there after that sort of stage of sort of time, just after that stage of timing, but people were exploring. There were other groups on various islands all around it. You remember Lahir was booming along. Of activity in this sort of general Southwest Pacific. Just to the north of Kosh, you got the Philippines with all the exploration that's going on with porphyry and epithermals up in there. So it was a case of people getting into areas that they hadn't had exposure to before and didn't know, what the exploration potential was going to be. A huge amount of grassroots works to begin with. But after that whole Busang situation, I think, yes, people took a step back, the big mining companies still had a vision. They were looking at from a tectonic age, rock difference, ore deposit potential side of view to get into an area. It was basic, and you have to appreciate the whole Busang story happened basically in what was almost like a drill out, right? It was they made some discoveries and then they started sticking wax of holes down, and then the whole sampling situation happened after that. That wasn't based on green fields or reconnaissance exploration, which is what would have been going through these districts or these islands, et cetera, in the first place.
All right. I think should we call it? Should we let Bruce off the hook?
Yeah, we're getting close to nearly 2 hours now. Thanks so much, Bruce, for hanging in there with us and answering so many questions.
It was a marathon run.
My pleasure. I enjoyed it, and I hope the audience enjoyed it too.
Yeah, definitely. There was an earlier kind of comment asking, do you have a reference list perchance that you can let us know later, and we can always.
Sure. Yeah. Look, I was thinking of putting that onto a slide at the end of the talk, but I must admit I just didn't get around to doing it. But I can certainly do that. And should I send it to you, and you can stick it on the website or something?
Yeah, that would be great. We can actually just put it on at the end of or below the presentation. For anyone who's great. Thanks so much. And are you okay? Like, there might be some. I think there's one or two more questions in there, but I think it's definitely time to finish up now. If they send you an email.
Yes, of course, absolutely.
Okay, great.
Contact details are there at the end of the talk. If anybody would like to get in touch with me for anything, I'm happy to help them if I can.
Fantastic.
Awesome. Well, you did a marathon run. It was a great talk. We had a good turnout. Everyone was interested. That's the best. So good. I mean, thanks everyone for coming out, and thank Bruce as well. The most.
Thank you guys for organizing. This is great.